Okay, hey everybody, so we're finishing section 10.3 now, and what we did in the first video for 10.3 was a little specific. That's probably not the way we would choose to normally do that problem, but what we're about to do in 10.3 is simplify some trig expressions and verify trig identities, which we'll talk about what that actually means in a second. And that we're going to be doing a lot of, especially next year in pre-calc. So this is more like what you'll see, excuse me, a lot of using those formulas that we saw in the book. Okay, the first example we're going to see is asking us to simplify. And the first expression that we're shown is cosecant of theta, cosine of pi over 2 minus theta, plus cotangent squared theta. Now this should look like something from the book. Again, I'll give you these formulas on the test, but this is one of my cofunction identities. And given that I know that I'll have this formula, I can look and see that cosine of pi over 2 minus theta is equal to sine of theta. So I can start by just rewriting my expression, replacing cosine of pi over 2 minus theta with something that's equal to it, sine of theta. We can all agree that this is simpler than this, right? So I've taken a step in the right direction. The next thing I want to do is see if there's any canceling or simplifying that can be done here. And to do that, I'm going to rewrite everything I can in terms of sine and cosine. Now, sine is already in terms of sine, but cosecant is the reciprocal of sine. So I can rewrite it as 1 over sine theta. Remember, 1 over sine is the same as cosecant, times sine theta, which was already there, plus cotangent squared theta is the same as cosine squared theta over sine squared theta. Because one of my formulas says that cotangent is cosine over sine, and if it's squared, that squared just goes to the numerator and denominator. Now, this is a lot simpler, isn't it? The sines cancel, and I'm left with cosine squared over sine squared, which means I've got 1 plus cosine squared theta over sine squared theta. Now, rewriting cosecant in terms of sine over here did help me because I was able to cancel it out and see that sine over sine just equals 1. But rewriting cotangent squared in terms of cosine and sine didn't really help. Nothing seems simpler here than it was before. Instead, I'm going to think, you know what, that didn't really work out, and I'm going to leave it as 1 plus cotangent squared theta. And does this look familiar from our formulas in the book? Whenever I see a 1 or a squared trig function, it should remind me of these very commonly used Pythagorean identities. This one says that 1 plus cotangent squared theta equals cosecant squared theta. And so I know that 1 plus cotangent squared theta equals cosecant squared theta. My problem went from, let's see, kind of a mess to something pretty simple. I'm all done. I've simplified. Okay, let's try one more simplification problem. Cosecant squared x minus cotangent squared x over sine of negative x times cotangent x. Okay, just like in the last problem when I saw cosine of pi over 2 minus theta, and I thought right away of my cofunction identities. When I see sine of negative x, I need to think right away of my negative angle identities. And I can look and see that sine of negative x is equal to negative sine of x. Sine of negative x equals negative sine of x. It's nice if the angle, so what I'm taking trig functions of, is the same angle, x, 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 and x, for all my trig functions. Here it wasn't. I had 3 positive x's and 1 negative x. And in the previous example, I had theta and theta, but here I had a different angle. I had pi over 2 minus theta. And so my first step in both problems was to change it, if possible, so that all the angles were the same, theta, 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 and x, 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 x. All right, what can I do now? Well, I'm not sure, and so I'll try rewriting everything in terms of sine and cosine. Cosecant is 1 over sine. So cosecant squared is 1 over sine squared, minus cotangent is cosine over sine. So cotangent squared is cosine squared x over sine squared x, over negative sine is already in terms of sine, and cotangent can be written as cosine x over sine x. Sometimes when I'm dealing with all these fractions here, it's helpful for me to write sine as sine over 1, just to help me see here are the numerators, here are the denominators. And right away, I can see that my sines cancel. On the numerator, any ideas what I can do to simplify these two terms that are being subtracted from each other? If I want to subtract fractions, I have to have a common denominator. And look, I already do. Sine squared is my common denominator. And on the numerator, I've got 1 minus cosine squared x. So there's my rewritten numerator. And down here, the signs canceled, and my rewritten denominator is negative cosine x. Okay, this next part is pretty cool. 1 minus cosine squared x should remind me of my Pythagorean identities. Whenever I see squared trig functions and 1s, I think of my Pythagorean identity. Which Pythagorean identity is it that has cosine squared? It's this one. Sine squared x plus cosine squared x equals 1. The problem is, I don't see 1 minus cosine squared x in this identity. I have to actually rearrange this formula to get it. If I subtract cosine squared from each side, I get sine squared x equals 1 minus cosine squared x. And now I can see that 1 minus cosine squared x can be rewritten as sine squared x. Let's do it. So I've got 1 minus cosine squared x, which I'll rewrite as sine squared, over sine squared. And on the denominator, I still have negative cosine. Well, that worked out really well, because now sine squared over sine squared is just 1. One over negative cosine x. My last step is, rather than leaving it as a fraction, I know that 1 over cosine is equal to secant. Okay, so these problems can be tricky. You have to be really familiar with your identities. You have to be able to know your Pythagorean identities by heart, and you need to recognize when there's an expression that comes from one of your Pythagorean identities. You need to know your reciprocal identities and tangent and cotangent identities by heart, so you can quickly rewrite cosecant as 1 over sine and cotangent as cosine over sine. And then you just need to be really good at algebra. You need to know how to combine fractions, how to, cross off something from the numerator and denominator. This one we didn't end up needing to, but if I'd been dividing by another fraction, that's the same as multiplying by the reciprocal of that fraction. So there's a lot going on, okay? And we're going to use all those skills for the next kind of problem, which is called verifying trig identities. Verifying trig identities is a really fancy way of saying, prove that this formula is true. So you're going to be given a formula, 2 minus cosine squared theta equals 1 plus sine squared theta is the first one we'll do. And you're going to be asked to prove that this is a true statement. Okay? This is not asking us to solve for theta, which is normally when we have an equation in a problem. In the past, what we've usually been asked to do is solve for theta. What could theta equal? That's not what we're being asked to do here. We're actually being asked to show that this is already completely identical to this for all values of theta. Okay? Now, there are some tricks that we're going to do when we verify trig identities. One of them we've already done a couple times in simplifying. It's not always the first step, but it often is. Rewrite everything in terms of sine and cosine, because it helps us see opportunities to cancel stuff that we might not have noticed otherwise. Another thing that we've already done a little bit of is working with the fractions we have. Sometimes we have a fraction like this, 2 terms on the numerator and a single on the denominator, and we can split up that fraction, a over c plus b over c. And sometimes we'll be doing that in our trig functions. Sometimes we're given these two fractions, and we need to combine them using a common denominator. Okay, it's like going from here back to that. Of course, we know how to multiply fractions. We multiply straight across. And dividing fractions is something that comes up a lot too. A over b over c over d means I need to take the top fraction and multiply by the reciprocal of the denominator. So I get AD over BC. Okay, so write everything in terms of sine and cosine, work with fractions. Another thing to do that we've already done a little bit of is look for your Pythagorean identities. If you see squared trig functions and ones, it's a good indication that you're going to need to use a Pythagorean identity. Look for your cofunction identities. Whenever you see one of these, that's probably a cofunction identity. And look for your negative angle identities. Whenever you see one of these inside of sine, cosine, or tangent, it's probably a good indication you're going to use your negative angle identity. The last one is the trickiest to use. We're going to do it in our second example. Multiply by the conjugate. So I'm going to leave that for now, and when it comes up in our second example, I'll show you what that means. Okay, so let's start by verifying this trig identity. When you're verifying a trig identity, remember, you're not solving for theta. In fact, unlike equations, you can't do unto one side what thou dost unto the other. Okay, that golden rule of mathematics doesn't apply to identities because you have to think of the left side of the equation as its own problem and the right side of the equation as a completely separate problem. And you need to pick either the left side or the right side and rewrite it until it looks like the other side. You can't, like, for example, subtract 2 from both sides. That doesn't work for identities. Okay? It takes some getting used to. So let's start. Sometimes it's difficult to know which side to start with. If one of the sides is more complicated, we usually start with that side, but these are both pretty simple, so I'm not really sure. I'm going to start with this side, 2 minus cosine squared theta. Now, I know that when I see squared trig functions, I might be able to use my trig identities. And we saw in the last problem that 1 minus cosine squared x equaled sine squared x, right? Is there any way I could rewrite 2 minus cosine squared theta so that it was 1 minus cosine squared theta? Well, let's see. 2 is 1 plus 1, isn't it? Now look what happened when I split up that 2. Now I have 1 minus cosine squared theta. We've already seen from the last problem that 1 minus cosine squared theta is the same as sine squared theta. So I can rewrite this as, instead of 1 minus cosine squared, sine squared theta. And now look, the left side is identical to the right side. I didn't do anything on the right side. I only worked with one side by itself, but I simplified it or transformed it so that it looked like this. And in doing so, I've verified that this identity is in fact true. So I'm done. Okay? These aren't the kind of problems where you're answering some unknown question. You're not going to be asked to verify an identity unless it's true. But your work in showing that it's true is what I'm going to be looking at. Okay? These are a little bit like proofs in geometry. The good news is, unlike geometry, you don't need to list, the reasons for each step. Commutative property, transitive property, CP, stuff like that. Instead, you just need to show your work. There's another way we could have done this problem. Let's say that I didn't think of splitting up that 2. Instead, I was just stuck and I said, you know what? On the left side, there's a cosine squared, and I know that it needs to become a sine squared. What equation relates cosine squared and sine squared? My Pythagorean identity. How can I rewrite cosine squared in terms of sine squared? Well, I'll isolate cosine squared here by subtracting sine squared from both sides. So I get cosine squared theta equals 1 minus sine squared theta. And let's say that I start my problem by replacing cosine squared theta. Instead of doing this, which was perfectly good, instead of doing this, I decide to start my problem by replacing cosine squared theta with 1 minus sine squared theta. So I'd have 2 minus 1 minus sine squared theta. Now, the negative would need to distribute to both terms, so I'd have 2 minus 1 plus sine squared theta. Combining my like terms, 2 minus 1 is 1 plus sine squared theta. And once again, I've transformed the left side to equal the right side. Okay? Look, this is a perfectly good answer, and so is this. In fact, there are going to be lots of different ways to do these trig identities. As long as you're mathematically correct, and you change one side so that it looks like the other side, then you're done. Okay, let's do one more. Verify the identity. Sine x over 1 minus cosine of negative x. Oh, as soon as I see that, I think this is probably going to be that negative angle identity. Equals cosecant x plus cotangent x. Now I need to decide which side I want to work with. And usually you want to work with the one that you have some idea of what to do with it. And since I've already noticed that this is a negative angle identity, and since the left side's a little more complicated looking altogether, maybe I'll work with the left side. Cosine of negative x is the same as just cosine of x. So I can rewrite the left side like this. Now, at this point, I've got a fraction, and there's a 1 minus cosine x on the denominator. Here's where we get back to that last tip. Multiply by the conjugate. When you have often a fraction in your identity, and you've got a 1 minus cosine x or a 1 minus sine x, or for that matter, a 1 plus cosine x or 1 plus sine x, it's often helpful to multiply by the conjugate of this binomial. Remember, the conjugate of a minus b is a plus b. It's the same two terms, but instead of a minus, it'll be a plus. Now, I can't just multiply by anything and expect it to stay the same. I can only multiply by 1. So if I multiply by 1 plus cosine x on the denominator, I have to multiply by 1 plus cosine x on the numerator too, because this whole thing is just equal to 1, and multiplying by 1 doesn't really change this. Okay, on the numerator I've now got 1 plus cosine x times sine x. And on the denominator I've got a plus b times a minus b, which you recognize as a factored difference of squares. When I FOIL this out, I'm going to get a squared minus b squared. 1 squared is just 1, isn't it? 1 minus cosine squared x. Where have I seen that before today? That's right. That's sine squared x for my Pythagorean identity. 1 plus cosine x times sine x. Notice that each time I write a next step, I rewrite the entire expression so that everything I'm writing is equivalent to the last thing I wrote. So 1 minus cosine squared x is equal to sine squared x. This is sine over sine squared. So when I cancel out the sine on the top, it cancels out one of the sines on the denominator. And I'm left with 1 plus cosine over sine. Now this may not look a whole lot better than what I started with, but it really is, because now I can split up this fraction. 2 terms on the numerator, a single term on the denominator. I can think of this as my common denominator and split up the fraction. So this can be rewritten as 1 over sine plus cosine over sine. 1 over sine, I know, is cosecant, and cosine over sine is cotangent. Cosecant x plus cotangent x is the right side of the problem, and so I verified the identity. I'm done. This is an example of a more difficult one. They won't be all this bad, okay? Or this fun, I should say. All right, so that's it for today. Let's see, what are the problems I was going to assign you? Here they are. The problems that I'd like you to do and bring into class tomorrow are page 631, 3, and 11, and I'll show them to you here. Page 631, number 3. Okay, find the value of the other 5 trig functions of theta if sine theta is 1/3 and theta is between 0 and pi over 2. Number 11 asks you to simplify, and there's the answer, negative tangent theta, so you can check your work. The original expression is sine of negative theta over cosine of negative theta. These are both pretty quick problems, and when you come into class, we'll work on some of these identities, which can be a little tricky. All right, I'll see you then.